Alright folks, I thought we would just go over everything. Is that okay? Like have a complete review of all this stuff. It'll be kind of fast, but and if you feel like we need to stop for a particular topic, please do stop me, okay? And we can go over it. You can see this okay? This works for you, okay? Yeah? Alright, so remember I sent out the list of topics. We have these topics. For capacitors, we're going to have just sort of basic capacitor stuff, and then we'll also have capacitor and circuits. Alright, we'll have Ohm's law, we'll have power, we have resistance. That's the whole thing about the resistance being proportional to the geometry of the material and the resistivity, all that business. We'll work through some problems like that. And then also resistance defined by Ohm's law. Let's see, we had resistors in series, parallel, and combination circuits. All right, we'll work through examples of all of those. And then also we had household circuits. All right, these I had about 8 to 9 questions for capacitors. And then the rest of these collectively about 16 questions. Okay, so there's more weighted towards the resistors, but we sort of had more topics in that. All right, let's look at capacitors. We had a couple things. First of all, let's probably go back to that. For capacitors, you need to know these relationships that Q is equal to CV, and then C is this kappa epsilon naught A over D. All right, you need to know how these are related. So like, for example, we had a question like this, where if I have, actually we had a series of questions like this, where if I have a capacitor that's hooked up to a battery, say it's hooked up to a 100-volt battery, and I have a certain capacitor, and then I take it off of that 100-volt battery, and then I want to know if I change, say, the area of the plates, I increase the area of the plates by a factor of 2, what happens to the voltage? You remember this question? We had one similar to this. In fact, we had a whole series of questions like this. So if I have this capacitor hooked up to this 100-volt battery, that gives it a certain amount of charge, and then when I take it off of that battery, that charge remains constant. Okay? Right. And then if I change the area of the plates, that changes the capacitance of the capacitor. It changes its capacity to store charge. And if I do that, that's going to change the voltage. So let's step through this process because we had several questions. You'll likely see a question like this on Monday. All right, so when I have it here, if I take it off the voltage supply, that charge is going to remain constant. So when I put a line over, that just means it remains constant. And I want to know what happens if I double the area of the plates. If I double the area of the plates, that's going to double the capacitance. So if I double the capacitance here, what has to happen to this voltage in order to keep the charge constant? It has to be half. So I have to have a factor of a half. So that means when I measure this voltage across this new capacitor, it's going to have 50 volts. All right, so you'll have some questions like that, sort of basic ideas. What happens if I change the properties of my capacitor, either the area or the distance between the plates, or the what's it called? The dielectric, right? The material in between the two plates. That's this kappa right here. We didn't deal too much with dielectrics, but remember it increases the capacitance if I put something in between.
And what's that epsilon?
Epsilon naught is a constant. It's the permeativity of free space. It's on your equation sheet. It's 8.85 times 10 to the minus 12. It's like, well, what is it? It's farads over meters, I guess. Yeah, farads per meter. All right? But that's on your equation sheet. Okay? You'll also have just some basic, I give you the area, I give you the distance, I give you kappa, and I ask you, what is that capacitance? That should be pretty straightforward, I hope. I mean, you have the equation, you just have to put the numbers in correctly. Okay? Yes, straightforward? Okay. And then you'll also have some circuits. Let's just do a couple of examples. Let's just do a straight up series circuit, and then I'll do a combination circuit. The parallels are pretty easy, so I'm just going to do a series and a combination. Let's say that, actually first let me recap the rules. You might see some questions just about how resistors and or capacitors act when they're in series or in parallel. And you need to know these rules anyway, so just make sure you got them. So for caps in series, this is just for capacitors. They have the same charge. The equivalent is 1 over C1 plus 1 over C2. That's on your equation sheet, by the way. For capacitors in series, Q equals CV. That's true for parallel too. And, for caps in series, V is equal to V1 plus V2 plus ... That means that, like for example, if I have 12 volts here, I have to have 8 volts and 4 volts. Or if I have 12 volts here and 8 volts here, that means I must have 4 volts here, because they have to add up to equal to 12. That rule is also true for resistors. For caps in parallel, they have the same, not charge, but voltage. The equivalent is just a sum. Q equals CV. And that's it. There is a rule too that the total charge, the equivalent charge, is equal to Q1 plus Q2. It's not very useful though. Okay? So those are the rules. Make sure you know those for capacitors and then those for resistors as well. We'll go over the ones for resistors soon. So let's look at this circuit. Let's say that I have two capacitors. Let's say it's 3 microfarads, 6 microfarads, and I just want to know the voltage across each of those. Okay, when you have capacitors in series, what you have to do is you have to find the equivalent capacitance, and then find the equivalent charge, and then capacitors in series have the same charge, so I know whatever charge is on the equivalent capacitor will also be on each individual capacitor. So this equivalent is going to be what? A 3 and a 6 in series is going to be 2. That's right. So I find the equivalent is going to be 1 over 3 plus 1 over 6. That's equal to 2. Do y'all know all the little fractions that I gave you? Do I need to give them to you again, or you got them okay? Okay. It'll be useful to know those numbers. It'll make you go much faster, so you don't have to sit and think, well, it's a third plus a 6 and all that jazz. So my equivalent is 2 microfarads. So 2 microfarads, 12 volts. That means that I have a charge equal to 24 microcoulombs on that. That means I have 24 microcoulombs here and 24 microcoulombs here. Because capacitors in series have the same charge. So I'm going to have the same charge on each of those capacitors. And now that I have the charge and the capacitor, I can find the voltage. V is equal to Q over C. Be very careful with these because Q, which is the charge, has units of coulombs, which looks like a C. So you might get those confused. So be careful that charge is in coulombs and that we use the variable Q to represent it. You understand what I'm saying? All right, so capacitance is farads. So V is Q over C, so I have 8 volts here and 4 volts here. That's 24 over 3 and 24 over 6, 8 and 4 volts. It'll help you if you can just think about the relationship between these charges, between the capacitors. The 3 microfarad capacitor is half the capacitance of the 6 microfarad capacitor, and so it's going to have twice the voltage. It's different for resistors, but for capacitors, since Q equals CV, if C goes down, V goes up. Excuse me. For resistors, if the resistance goes up, the voltage goes up. All right, let's do a combination circuit. And we're just sort of doing all the topics, so but if you want to stop, we can. All right, a combination circuit. Can I go down from here? You'll certainly see a combination circuit, probably have a couple questions attached to it. Could be something like this, could be something a little bit different. Let's do this one. I don't know, let's do 4. Wait, no. All right, I want to know, I don't know, I just pick one. Let's say I want to know the voltage across this capacitor. Now, hopefully, by now, you might be able to just look at this and determine what is the voltage across that capacitor. Because the 4 and the 4 on the top, that's this one right here and this one, that gives me 2. Like 1 over a fourth plus a fourth is 1 over a half, which is equal to 2. And then the 2 and the 4, hey, everyone. And then the 2 and the 4, so these two combine to give me a 2 microfarad capacitor. And then this capacitor combined with this capacitor gives me what? They're in parallel. Gives me 6. And then 6 combined with 3 gives me what? 2. Right, so the equivalent there is going to be 2 microfarads. Let me redraw this just a little bit. So there's my 3. There's my 2 microfarad. That's this one that I drew up here. And then there's my 4. This is 12 volts. Okay. And then I can combine these two, and that gives me 6 microfarads. Be careful, right, because the rules are different for resistors for equivalent. Now, fortunately on the test, the first 8 or 9 questions are going to be capacitors, and then you'll shift gears and go into resistors. So do what you got to do to make that transition. All right. So I can redraw this new circuit. I have a 3 and a 6 in series with one another. And this is 12 volts. We just did that one, right? That's just like the circuit that we just did. And so if I want to know the voltages here, I have what here across the smaller one? I have 8 volts here and 4 volts here. All right. So remember to go back, I would go back and I'd find the equivalent capacitance of this, which is 2. That 2 microfarad equivalent capacitor would have 24 microcoulombs. So I'd have 24 microcoulombs here and 24 microcoulombs here. 24 divided by 3 is 8. 24 divided by 6 is 4. So I have 8 volts and 4 volts. So that's my 8 volts and 4 volts. And I'm looking for the voltage here. So if I have 4 volts on this capacitor, I also have 4 volts here and 4 volts here. All right. Recognizing that this 4 microfarad capacitor is the same as this one, so the answer is 4 volts. It has what charge on it? What is it? On this capacitor, what charge do we have? Well, it has 4 microfarads and 4 volts. 16. Right. Anytime you get 2 of those quantities, you can get the farad. So Q is equal to CV, so it's 16 microcoulombs. Okay, and I have a couple questions about combination circuits, like that. Okay. I could also ask you, well, let's just do this while we're here. What is the voltage across this capacitor? If I have 4 volts across this equivalent, how does that fare over here on this capacitor? It's going to be 2, Yeah, it's going to be 2 volts here. Reason is because I have one 4 microfarad and another 4 microfarad. They're in series, so they split up that 4 volts. So I get 2 volts and 2 volts. Only because they're identical do they split up that.
So even if they weren't identical, they wouldn't?
If they weren't identical, no, it wouldn't work that way. It would work the way that we did it up here. See, these two weren't identical, and so they didn't have the same voltage. Capacitors in series always have the same charge. If they're identical capacitors, then they'll also have the same voltage. They always have the same charge. Okay? Okie dokie. All right. Let's do, we can come back to this, but I want to cover all the topics. But like I said, if y'all want to stop me, that's okay too. But let's see, what was the next topic after that? Ohm's law. You need to know ohmic versus non-ohmic, right? Ohmic just means that it follows Ohm's law. We had a couple questions like that. So if I increase my voltage by a certain amount and my current increases by the same amount, then that's an ohmic device. So like for example, if I double my voltage and my current doubles, then that's an ohmic device because it follows Ohm's law. Let's see, what else can we do? Just a basic, current as well. So also wrapped up in this, you need to know the definition of current. I is equal to Q divided by T. We had some problems like this in some of the old tests. Just give you a basic circuit here. I have, say, 12 volts. 2 ohms, and I want to know, I don't know, in 1 minute, how much charge passes through that resistor. In that, you would have to find the current through a 2 ohm resistor with 12 volt battery. Gosh, what would that current be? I know V is equal to IR, so my current I times 2 has to be what? Equal 12. Right, it has to be 6 amps. So I is equal to V over R. That's 12 volts over 2 ohms, which is 6 amps. And then if I want to know the charge, I come back over to this expression. This is on your equation sheet, but you need to know how to apply it. And if I want to find Q, that's going to be my current times my time. Be very careful, my time here is 1 minute, but in the SI system we use what? Seconds, right? We had some questions like this, so it would be 6 amps times 60 seconds would be 360, excuse me, coulombs. Okay, something simple like that. I think that should be, like, if you're on your toe, like, just not making any mistakes. It's always the hard thing, right? Making mistakes. Okay, let's see, so power as well. To understand power, we had power is equal to V times I. Trying to think. We had a series of questions where, we have resistors and let's say we have 2 ohms and 4 ohms and 12 volts here. What is the power dissipated across these? Well, you could find that pretty simply. You could figure out what is the current. In this case, I have 6 ohms with 12 volts. So my current is equal to V over R, which is 2 amps. And then I could find the current across each of these. My power. Now power is equal to voltage times current. And so I would have to find my voltage across each of those, which I could do. Or I could also say that P is equal to I squared times R. That's just an alternate expression for the power. You get it from substituting Ohm's law into the power equation. It's also on your equation sheet, so if you just want to use it there. And so I could find my power here for this one is going to be I squared, that's 2 amps squared times R, which is 2 ohms, and that's equal to 4 times 2, or 8 watts. And then you could do a similar thing for this one. It would be 2 amps squared times 4, which would be 16 watts. All right. We'll come back to power. There's not a whole lot on it about power, but we'll come back to that. Let's see what the next topics were. Okay, yeah, so you also need to know about resistance. We had a couple things for resistance. Resistance is defined by Ohm's law as V over I, but then resistance is also the resistivity times the length over the area. We had a couple problems, like for example, we had one where I give you the voltage and the current for a particular material, and then you have to figure out, and then I also give you the dimensions of that material, and you have to go and you have to figure out what is the unknown material. Remember working that? Had a little table with all the metals. You'll see a problem like that on Monday, where you have to figure out what is the unknown material. So in order to do that, like let's say for example, I have a material with a certain length, a certain area, and a certain voltage and a certain current. First, I would solve for R, and then I would solve for rho, which is RA over L, and then I would get some value, and then you can just pick it from the table. We can look at some numbers later. We'll look at some old tests once we go through all the topics. You'll have resistors. I think that was the next topic. You have resistors in series and in parallel. So for resistors in series, let me just write down these rules. We have a similar set of rules. Resistors in series, they have the same current. They always have the same current, resistors in series. For resistors in series, the equivalent resistance is the sum of all the individual resistors. For resistors in series, V is equal to IR. That's true for resistors in parallel. And then also resistors in series, the voltage is equal to V1 plus V2, which is the same for capacitors in series. For resistors in parallel, you have the same voltage. The equivalent looks like that. V is equal to IR. And then also, this is the junction rule, which we're going to get in class later, that the total current entering a junction is equal to the sum of the currents going out of a junction. So those are our rules. You need to sort of have an understanding of how these are applied to circuits with resistors. All right, let's do some problems. Let's do a series problem. Again, the parallel problems are pretty simple, but you could see a parallel problem. Like not all the problems, some of the problems are pretty straightforward. Some require more steps. Well, let's just do a simple series problem. Let's do 2 ohms, 2 ohms, and 1 ohm, and 10 volts. And I want to know the current and the voltage on all of these. Now I know that for resistors in series, they have the same what? Voltage or current? They all have the same current, right? Because whatever current comes up through this wire has to go through each resistor because they all come one after the other. All right, so whatever current is going through the equivalent resistor is also going to go through each individual resistor. So I first want to find what is the equivalent of all three of these, and the equivalent is equal to 2 plus 2 plus 1. For resistors in series, that's 5 ohms. And so I can redraw this if I wish as a 5 ohm resistor and a 10 volt battery. And so that tells me that my current is 10 volts over 5 ohms. That's V over R. That's 2 amps. So I know that for each of these, I have 2 amps, 2 amps, and 2 amps going through those. All right, so then if I want to find the voltage, anytime I know two of those quantities, I can find the third. V is equal to IR. That's 2 amps times 2 amps. That's 4. The middle one also has 4, and the third one has what? 2. Right, so I have 4 volts, 4 volts, and 2 volts. And fortunately, 4 plus 4 plus 2 is equal to 10, as it should. Right, this number should be equal to this number. That's a pretty good basic series circuit, but you could see something like that as well. All right, let's do a combination circuit. You'll see, I think there are 3 or 4 questions that were related to combination circuits. You had one where I give you a circuit, and I ask you, you know, like what is the equivalent resistance? And then I ask a follow-up question, what is the voltage or the current on one of these resistors? So let's do one like that. And then you have a couple of others, just sort of different circuits. I try not to give too many of those series, like follow-up questions. All right, so let's say that I have a circuit similar to the capacitor circuit I did before. I'll say this is 12 volts. Actually, no, let's do a different one. Let's do one of those like we did in some of those different ones. I want to know what this equals if this equals 8 volts. So the voltage on this resistor right here is 8 volts, and I want to know what is the voltage on the power supply. So in order to do that, at first I just want to figure out what is the equivalent. All right, so let's redraw this. I have my 4 ohm resistor here. I have a parallel branch here. This top resistor is what? It's 4 ohms, right? That's because I combined these two 2 ohm resistors. 2 plus 2 is 4, and then this bottom one is 4 ohms. All right, I can combine these two. 1 over a quarter plus a quarter, that's equal to 2. Two ohms, 4 ohms. All right. What then is my voltage across the battery? All right, well, I know that the voltage across that 4 ohm resistor is 8 volts. So what then is the voltage across this resistor? What do y'all think?
Whenever you had it with the 4 and 4, both of those were 8 volts.
Mm-hmm. Yeah, that's right. Y'all are all right. So because this is 8 volts, this is 8 volts, that means this also has to be 8 volts. You know what? Because resistors in parallel, they have the same voltage. So I'm also going to have 8 volts here. All right. So coming back here, if I have 8 volts across this resistor, what then is my voltage across this resistor? This is a resistor that is twice the 2 ohm resistor. So what is the voltage? Is it 4 or 16? You're right, at 16. So it's 16 volts. If you forget, you can take this data that you have, and you can find the current through this resistor, which is 8 over 2. That's 4 amps. And then if I have 4 amps here, that gives me 16 volts. Right. So if I have 16 volts here, 8 volts here, what is this voltage? 24 volts. So you'll have a question something similar to that, and it'll require you to break down the circuit into, or to simplify the circuit into its equivalents, and then to think about how the voltages or the currents are distributed across that circuit. But that's a good type of question that you'll have. Oh, let's not forget about internal resistance too. That's a good application of the loop rule. Internal resistance, this equation is on your equation sheet, but if I have can I go down from here? If I have a battery, it has terminals like this. Remember we sort of described it as an internal resistance and then an ideal EMF source. All right, and then we measure our delta V. So let's say that my ideal EMF source is 12 volts. I have an internal resistance equal to, this by the way is epsilon. My internal resistance, let's say, is 1 ohm. And then let's say that I want to know what is this if I have a certain current. So let's say that my current is, I don't know, 2 amps. What is my terminal voltage, we call it? All right, my terminal voltage is equal to the EMF, that's the ideal EMF of the battery, minus the potential drop across that internal resistance. That's 12 volts minus 2 amps times 1 ohm. That's 12 minus 2, or 10 volts. So that would be my terminal voltage. This relationship is on your equation sheet, but just be aware of it. All right, so that's combination circuits, batteries. This is Ohm's law, sort of loop laws kind of thing. And then the last topic is home circuits. So there are several things that we went over regarding home circuits. Can I go down? All right. First, your house is laid out in parallel. All right, so that means that all have the same voltage. All things have the same voltage. All right, as I add as I add devices, the total current goes up, right? Remember, if we have resistors in parallel like this, the total current, which is this current, if you add more resistors, that total current is going to increase. So as I add devices, the total current goes up. If I add devices, the voltage for each device is the same. It remains the same. That's why household circuits are laid out in parallel, so that everything operates at the same voltage, at 120 volts. Let's see, I think that's all. Yeah, so if you look back at the old test, you'll see some questions where it gives you a series of statements about household circuits. That'll help you to prepare. So you need to know these basic ideas about household circuits. They're all laid out in parallel. And then we have 3 safety features that you need to know how to describe and know what they are. There were the GFCI, the grounding on your, like the third prong on your outlet, and circuit breaker. You need to know what each of these does. They're a little bit similar, so you have to be careful. The GFCI shuts down your device if the ingoing current ever exceeds the outgoing current. Right? It measures the current that's going into a device, and then it measures the current that's coming out of the device, and those should always be equal. But if that incoming current is ever larger, then it shuts it off, because that means that you have current that's going somewhere else that it's not supposed to be. That's very similar to the circuit breaker, but different. This shuts down the whole circuit if the total current exceeds some safe amount, whatever your circuit breaker is rated for. So if your circuit is rated for 15 amps, that means it shuts off if that total current, as you add devices, your toaster, your hairdryer, your radio, all that, if it exceeds whatever that safe amount is, it shuts off. So students often get those confused. Just be careful. Remember, the GFCI is comparing 2 currents, and the circuit breaker is just measuring 1 current, and it shuts off if it exceeds that current. The ground, it just provides a clear path to ground. And what that does is it protects you if somehow your device should ever become electrified, like if you have a loose wire that touches the case and the case of your device becomes charged, like your computer or whatever, then that extra electricity will go to that rod that you have in the ground outside your home instead of through you. Okay, the big ones that students get messed up on are GFCI and circuit breaker. And then one last thing regarding household circuits, and we did this on one of the quick tests, but if you have a series of devices on a circuit breaker, let's say you have, I don't know, a 1200 watt hairdryer, a 360 watt refrigerator, and a 120 watt light bulb, and everything's working just fine, and then somewhere you plug in, say, a 480 watt whatever, it shuts off. And so the question is, what is the rating of the circuit breaker? So you want to find the current for each of these. I is equal to P divided by V. V is equal to 120. So 1200 divided by 120, that's 10 amps. 360 over 120 is 3 amps. This is 1 amp, and this is 4 amps. So somewhere in between these 3, which is 14 amps, and adding this fourth one, this 4 amp one, which is 18 amps. So somewhere in between 14 and 18 is where your circuit breaker is rated for. So for example, I would give you 13, 15, 19, and 24, or whatever. What would be the right answer? That would be 15, because it's the only one that's in between 14 and 18. We had a question like that in class. This is how electricians, they build electric circuits to make sure that you don't exceed the safe capacity of the circuit. That is everything on the test, I think. Let me just go back and double check. Let's see, home circuits. Yep, that's everything on the test. So, are there particular things that y'all have trouble with?
I mean, like, it's not so much just the math, because I know, like, especially the quizzes that we take, especially a couple, like the concepts of it. Like, I don't know, like, especially when you get circuit, and it's not like the math, you're just like, okay, the resistance is, I don't know, like, you take, I don't know if you, like, do one resistance thing, what happens to, like, the voltage?
Oh, yeah.
Yeah, I just get confused, like, what's, I don't know.
Okay, let's look at some of those. Yeah, those are good questions, because you will have some conceptual problems like that. They're not all. Let's look at this circuit. Simple combination circuit. Now let's ask ourselves some questions. All right, what happens to the overall current if we get rid of this resistor? So the first thing I ask, what happens to the overall resistance if I get rid of that resistor? What will happen? Will it go up or down? Right, the resistance will increase. Right, if I get rid of that resistor, the resistance, the overall resistance, will go up. Remember, resistors in parallel, when an electrical current comes to a parallel branch, it has options. And if you take away one of those options, then that means you're adding resistance, right? The electricity will have fewer places to go, and so your resistance is going to go up. So if my resistance of that branch goes up, what's going to happen to the total current here? Right, my total current will decrease. All right. Let's ask this: what if I get rid of that resistor, that same one? What's going to happen to my voltage here? Will it go up or will it go down? No, it's not going to stay the same. It's either going to increase or decrease. Well, let's think about it. So I know that this resistance right here will go up, right? So what's going to happen to the voltage across these resistors? If my resistance goes up, what's going to happen? Voltage goes up. Remember, I have a V equal IR. If R goes up, V goes up as well. All right. So if this V goes up, what has to happen to this V? If this one goes up, what has to happen to this one? It has to go down, because they both have to add up to equal the voltage here. All right. Let's try another question. You had one like this in your test. Let's say, I don't know, I gave you some resistors. Let's see. Which of these resistors will have the biggest current? That should be an easy question. Which of these resistors will have the biggest current? Right, this one right here. Because all of the current's going to go through this resistor. So that one clearly will have the biggest current. Which one will have the next biggest current? Or actually, no, let's ask, which one has the smallest current? The 6 ohm. Right. So if I imagine, excuse me, if I imagine that I have current that comes along through here, it comes up through here, it splits and goes these two ways in some way, and then it comes back over here, and all of it goes through that 1 ohm resistor. But then we want to think about how does it split through these two branches, these two parallel branches. All right, well, more of the electricity is going to go the path with the least resistance. Because a resistor does what? Okay, yeah, electricity flows in the path of least resistance, but more general is that resistors resist the flow of electricity. They slow down electricity. All right, so your current, more of your current is going to go through the smaller resistance. And conversely, less of your current will go through the bigger resistance. So I'm going to have the least amount of current going through this 6 ohm resistor. And then the next amount through the ones above. And we could go through and we could figure out all those, but it's useful just to be able to look at it and think about, well, this one has more current than the other. Let's see. Which one has the highest voltage of all these? No.
The one,
No.
The highest voltage.
Mm-hmm.
So once the series have the same, I mean, does it parallel have the same voltage?
You're right, Adina. Yeah. So this one will have the same voltage that is shared by these two. The 6 ohm will have the bigger voltage. You know that because I have a 6 and a 3. And a 6 and a 3 is a what? In parallel. Is 2, right? And so if I have a 2 ohm resistor and a 1 ohm resistor, the 2 ohm is the equivalent of those on the left. The 2 ohm resistor will have the bigger voltage by amount of 2, right? So for example, if this was 12 volts, this would be 8 volts. These would have 8 volts, and this would have 4 volts. Okay. Let's look at some old tests. Is that okay? Or we could watch The Avengers: Age of Ultron. I think that, yeah. If y'all see anything that you want to look at in particular, just let me know. Right now I'm looking for some of those. Anybody have any like that here? Okay, this is a good one. This is sort of like what he was talking about. So here, if I close this switch, that means, by the way, that, I add that resistor R3. What happens to the potential across R1? All right, when I add R3, what happens to the resistance of this branch? This resistance goes up or it goes down when I add that resistor R3. Remember, guys, resistors in parallel, when electricity comes to resistors in parallel, I have this current that's coming along. It gets up here and it says, oh, I have 2 options, right? If I add a third resistor, it says, oh, I have more options. That means there's less resistance. Okay, so for resistors in parallel, as I add resistors, the total resistance goes down. All right, so this resistance is going to go down. So what then is going to happen to the potential across R1? It's going to what? Right, it's going to increase. Because if this resistance goes down, that means this voltage goes down. And so this voltage has to go up in response. This is spring 13, by the way.
So if it was asked in regards to R2, then it would decrease.
Right. The voltage would decrease for R2. Right. The voltage would also increase for this one. Those two that aren't in that parallel branch, they would both increase by a certain amount. All right? Is that okay? Let's see. Any of these you want to look at? We're not doing multi-loop circuits, guys, so as you're studying for your test, if you ever find one that has 2 batteries in it, we're not going to do that. That's going to be next test. All right, let's look back. Spring 2012. Look, exam 1. You want to do one of these? Capacitor circuit? Okay, let's do this. Here, this is a series of questions. And just wants to know what is the equivalent first. Hopefully you can look at this pretty quickly and tell me what the equivalent is. I know this is 2 microfarads, and so the equivalent is what? The whole thing is 5. I just say 2 plus 1 plus 2. is 5. Because in parallel, they add up. In series, you got to do that funky 1 over business. All right, and then what is the voltage across C2? All right, I know that I have 12 volts. 12 volts. What is the voltage here? Remember, big capacitors have small voltages. Right, Q equals CV. So if C goes up, V goes down. It's different for resistors. For resistors, big resistance means big voltage. All right, but here, the 6 microfarad is going to have the small voltage. So what is its voltage going to be? 4. Right, I'm going to have 4 volts here and 8 volts here. 8 plus 4 equals 12. I know they're proportioned that way because the capacitors are proportioned that way. They have a 1 to 2 ratio, and so the voltages will have a 2 to 1 ratio. Follow what I mean by that? Okay, so here C2 was 4 volts. And what is the charge across the 2 microfarad capacitor? Is 24. I know C, I know V. I just multiply the 2 and I get 24. All right. How about this one? What's the charge across the 2 microfarad capacitor? No, C1 and C3 are in parallel. I can tell that because as I go along here, I don't see any breaks until I get to this point. And then I have 2 branches. And so I know then that this circuit looks like this. Where I have C2, C1, and C3. They certainly will have circuits laid out like this. Like most of your circuits are going to be laid out like this on the test, actually.
So C2 is just in series with the ones in parallel?
That's right. C2 is in series with C1 and C3, which are in parallel. That's right. The voltage across C1 is 6 volts. I know that because these two add up to 6 microfarads, and so I get an equivalent that has 2 6 microfarad capacitors, 6 microfarads, 6 microfarads, 12 volts. Because these are identical, I have 6 volts and 6 volts. All right, so that means I have 6 volts here, and these two share 6 volts, so they both have 6 volts. All right. Right, that's like one we did before. I used to go a lot faster. Students didn't really get it very well. Okay, I think we've done a lot of these. If y'all see anything that stands out, let me know. Capacitances. Anything in particular, y'all? Okay. This one right here?
Yeah.
Okay. Sometimes when you see circuit diagrams, they're laid out like this. It saves space when they're writing the diagram. This is just, it's the same as having a 3, a 2, and a 1 in parallel. So it's the same as. That's the same. Okay. You won't have one like that. We didn't really do that. All right. I think that's everything on the test. I'm willing to answer questions as we go, but that's sort of all that I have for now. I don't think that it's like I wouldn't expect any tricky things, so to speak. Like it's what we've done here, but you know what we've done here isn't easy, so it's still going to take a lot of practice. Usually people do better on this material than on the previous materials. That's good news, right? Like as a class, the class usually does better. Which I did darn well on that last test, so I don't know that you'll get a whole lot better than that. Like as a class. Very impressed, actually.
Like, because I took this class the first time taking physics again. It seemed like a third.
That's great. That's very good. Very proud. Yeah. And that was tough material. I don't know. I blew that exam out of the water. Okay. You have questions? Any more questions? All right. Well, if you're in the in-class section, we're going to have a review tomorrow. We'll do some similar things. Probably not as long, of course, because we're going to spend some time going over multiple circuits. I'll be available tomorrow afternoon if you need me, and then Monday as well. I'll be available before. Well, no, not really before class. Yeah, I have 7:30 class. Actually, their exam starts at like 7 o'clock or 7:15. It's nice. They like the extra 15, 20 minutes.
That is nice.
We'll probably be in the auditorium, but I haven't gotten confirmation yet. So.